in the International Center for Mathematical Sciences at the Institute of Mathematics and Informatics, the Bulgarian Academy of Sciences. He is leading a new group which was created this year on topological, computational, and algebraic complexity of complex systems. And he has created a team at our center which has started active work. And the conference that he is organizing with his colleagues is dedicated to the interaction between different branches of pure mathematics with machine learning, and with the idea how to advance research in different fields that are related to artificial intelligence, and how pure mathematics can help to study such kind of problems. He has also, I will repeat this with pleasure, decided to introduce within these conferences the so-called Atanasov lectures, which is very important for us Bulgarians, because everybody of you know probably that John Atanasov wasn't the inventor of the first electronic computer. It has Bulgarian origins, which were discovered many years ago. And one curious thing is that John Atanasov was first recognized here in Bulgaria before being recognized in the United States by the US president. And today he will speak about Algebra Avalanches, a public lecture which is within this series also of lectures. And it's my pleasure to give him the floor and to thank you very warmly on behalf of our colleagues from the Institute that he agreed to chair this important new group in our International Center for Mathematical Sciences. Thanks, Ernesto.
It is a great honor, of course, to be part of the International Center for Mathematical Sciences. We really believe in our mission. And this talk is dedicated to the people from the city of Sofia that are not at IMI or at all related to mathematics that came kindly to the public lecture. Thank you very much. I promise this talk will have no equations, zero equations, no, zero. And so it's, but it's also, I'm also attempting to do a progress report on the mathematical results that we have obtained since the inception of the group in June 2025. So there's a progress report of the results of the complexity group at the ICMS. And every result in the complexity group is an emergent result. It really an individual would not be able to have obtained a beautiful story. It's a story, what I'm going to say, it's just a story. And this beautiful story that I'm going to tell you today it was impossible to be obtained by an individual. It's an emergent phenomenon. And so I like to let's see if this works. There it is. So you're meant to imagine that this is Ocean's 11. And that we have the second one is Brad Pitt, of course, and now you can guess who and you can try to guess who am I supposed to be, but you know, you have to really stretch your imagination. In any case, so we are the team, and we're trying to do these hacks to obtain results in pure mathematics using the methods of applied mathematics. So people always say, apply the mathematics, the pure mathematics to the world. And we are doing this very perverse thing that we want to apply applied mathematics to pure mathematics. So this the inversion of reasoning that we're trying to apply. And so you've seen these pictures all over the posters and things, and approve. I have to approve. Someone's approving. Yeah. And you've seen this picture. So I have this problem. So look at this. It has a lot of detail here. It has a little ins. And on the other side, you can see what is in the little rectangle. So you pass it around. Look at it carefully. You first look at the other side, the round side, and then you look at the square side. So the team is Michel Shkolnikov, Turgai somewhere over there, Eugenio there, Constantino over there, Daniel in Mexico City, Alexander somewhere over there. Kevin is here somewhere. He's a young man, right? Pedro is almost as young, I think. Pedro is over there. And Edison is somewhere over there, also extremely young. And Nikita Karin is a great collaborator, and he's in China. So this is the bill, and the cat also helps very much. It's really been of enormous inspiration. In any case, we have, you have this situation, you've seen the cartoons, everything is barely stable, and then you put the last drop of water, the last grain of sand, and you have an avalanche. You have this huge event that occurs for this very infinitesimal cause. So there is an essential unpredictability in the situation, because how could you know that just by putting this tiny grain of sand at this tiny place, this huge avalanche was going to occur? All the grains have to be in these very complicated positions, friction, etc., etc. But we're interested in all walks of life in this kind of situation. Financial markets, historical events, etc., etc., etc. We're in physics, of course. We're very interested in this kind of phenomenology, where this very tiny accumulation of it, and then there is this final point in which you get this huge effect from a tiny action. And so we have the physicist define a model, a mathematical model. There is a mathematical sandpile. So what is a sandpile? It is meant to be a table made of in very tiny tiles, and at every tile you have a number of grains of sand, 2 or 3 or 1 or 5 or 10 or million, or doesn't matter, some grains of sand. And if the tower is too tall, like here, this is called stable. But when is this tall is 4 or more, we say that it's unstable, it's too tall. And so it donates 4 grains to its neighbor. They just go with equal probability to the 4 sides. And so this is what happens. You have this, and then this one donates. So this was 3 became 4, this was 1 became 2, this was 1 became 2, this was 2 became 3. But now this is too tall. And so this donates 2, 2, 1, 2, 2. I made a mistake or something.
No, it's okay.
And then, no, it's okay. Well, anyway, but, you keep it evolving. If it is taller than 4, you donate to the 4 neighbors. And if it is 3 or less, you do nothing. That's all you do. This universe, space is this lattice. Time is tick-tock, tick-tock. It's just that. And every agent, every elementary particle in the universe is a grain of sand. And there's only one law in this universe, the law that I told you. If your tower is bigger than 3, you donate to your 4 neighbors. You topple, you fire the barracks. Okay, so this becomes a universe that is evolving. This becomes an evolving universe. You have these tall things, and then they donate to your neighbors. And at the end you end with 1, 2, or 3. If you started with something very tall, a sign that goes off the table disappears forever. And now you end up with 1, 2, or 3. But of course, we are mathematicians, and looking at these grains of sand and counting them every time gets a little bit complicated. So we use colors, we use numbers. And this is the exact same movie made in colors. Except now that 0 is black and 1 is blue, and so you have this evolution, and you end up in the exact same state. It's the exact same movie as the previous movie. It's the exact same movie. But instead of little balls, we put colors, and the number of balls are encoded by a color. So, what happens when you put a few hundred grains of sand at the center of the table, and they start donating, and then the ones that get more than 4 start donating, and then the ones that get more than 4 start donating? Well, this is what happens. This is what happens when you do it at the center of the table. And you already see, even at this very small number of grains of sand, that you start getting these beautiful, symmetric, hypnotic patterns. You start to see some sort of mathematical structure, some sort of structure. And what you have been passing around, the prop, is what happens when you put 300 million grains of sand at the center of the table. At the end, you only have 4 colors. And, well, that's exactly what happens. You only have 4 colors. And if you put a 300 million grains of sand at the center of the table and you let it evolve, you get that picture. A mathematician trying to prove that this picture exists. Yeah, mathematicians are weird. So they're trying to prove that this picture exists. Is that picture? Is that? But if you are human, you are automatically fascinated by the richness of the geometry, structure, and it's almost a beautiful piece of art coming out of nowhere. I mean, I just put just one point with a lot of sand, and I let it evolve by itself with just one law of the universe. That law, that extremely simple law, nothing else. And this is the outcome. And this is a mystery. How come from this extremely simple law we have the arisal of this extremely rich structure? So, about 10 years ago, we decided to start thinking about this question at different latitudes and longitudes, and one converging to thinking about these things. So, if you close, I mean, in the prop you can see it in your hands, but if you close in, you see this extremely rich fractal structure, and you see these mysterious lines that you may not see, but you see it in the prop. You see these mysterious straight lines that mathematicians will call tropical curves, but I'll come to this later. So you see these beautiful straight lines. You zoom into the structure, deeper and deeper, you'll see this kind of picture, but it's ever more and more rich. This is the so-called scaling limit. This is the scaling limit. And in the researches that we have been doing in the following months, there is a recent proof, that the scaling limit exists. In these, there's no proof yet that the scaling limit exists. But in the ones that I will be showing, the ones that we have computed in a cluster here, Constantine, where are you? What's the name of the cluster?
Camus.
That cluster, that computer cluster, these ones that we have been computing in this computer cluster, all of them have a proof that the scaling limit exists, that these pictures exist. Okay, so they have so-called scaling, but it's a little bit like Zipf's law. You've heard of this. If you take any book, the Quixote, or Remembrance of Things Past, or the Bible, or anything like that, there will be this word that completely dominates, because this one is 10 times more than this. It's not a little bit more than this. And this one is, it's like earthquakes. This one is 10 times more than this, like the Richter scale for earthquakes. And then there is this word that will do a lot of the dirty work, and these words that give you most of the information. In fact, you can try this experiment on Google Books. Take just 3 lines of a book, but try that these 3 lines have a slightly strange word like quality. You say, is that a strange word? Yeah, it's not that common. It's like nearly every 3 lines will work actually in Quixote, for example. And then you look for these 3 lines in Google Books, and you'll nail the book instantaneously. You'll immediately know what the book is. Because it is these few words give you most of the information of the system. That is the book. This happens in biology. This is the metabolic rate of animals. This happens in knot theory, as we have been investigating with Pedro. We have been on knots. We have this complicated, we took this thing that's on knot, and we make this extremely complicated knotting of the thing. And then we want to unknot it. And then we have these cascades, these kind of avalanches of moves that occur seldomly, but that contain most of the information of the unknotting process. And we're doing it for very large amounts in polynomial time. And this picture was prepared by Pedro. And this expresses the complexity of this process that is trying to unknot a piece of code that is totally knotted. In any case, there's a big surprise for a mathematician. That is that you can add these things. You can add these things. So you have this configuration of sand that is relaxed. So I say that it's a configuration is stable if it finishes its relaxation process. It just dominated everything and is now relaxed. And now you have this relaxed configuration, and some configurations, as you add sand, if you think of it as a dynamical system, you put a grain of sand and you relax. You put a grain of sand and you relax. You put a grain of sand and you relax. You put a grain of sand and you let sometimes you get an avalanche, and sometimes you get a tiny thing. Most of the time you get a tiny thing. It's like the word "the." And now and then you get an avalanche. It's like the word epistemological that we will use. So sometimes you get this very common word. Most of the time you get this tiny thing, and sometimes you get these avalanches. And these are the states that appear infinitely often. So they are called recurrent states. And there is a theorem, a beautiful theorem that says that recurrent states form an abelian finite group, finite abelian group. So you add this one, and you add this one, you put the sand on top of the sand, and you relax. And then you get this other one. That's the addition, it's very simple. You just put it on top, one pile of sand, and you put the other one exactly on top, and then you let it relax. That's what you do. So it's kind of weird you are adding these things, but the theorem says that you can subtract these things meaningfully. In particular, it says that this group is a secret set of symmetries of something. So let's see, there's groups that numbers are groups because you can add a number 2 plus a number 3, and then you can subtract from 5, 3, and then you get back 2. It's all these things that you're used to, that numbers are a group, an abelian group. But there is these non-abelian groups that are the symmetries of a square, for example. This funny 4 means 4 sides. It just means that you have the symmetries of the square. All the symmetries of the square also form a group. Rotating like this is inverse to rotating like this. Rotating 2 times like this is inverse to rotating 2 times like this. Actually, rotating 2 times like this is inverse to itself. Because if you rotate 2 times and then you rotate 2 more times, you end up in the same place. So, in a group, it's very important that everything has an inverse. And that there is an element that does nothing, the identity element. In a group not doing anything, that's just leaving it fixed, that's the identity element of the group of symmetries of the square. That's the identity element. And often, mathematicians know, the identity is an extremely boring element. It's the easiest element in the world. In the integers, it's 0, the number 0. That's the identity. In this world, it's do nothing to the square. That's the identity. But in the Sandpiles world, this is the identity, and it's extremely hard to compute. So it's the only finite abelian group I know where the identity is extremely hard to compute. But you compute it. And this is a crazy thing, isn't it? You take any configuration of sand that is recurrent, you put this configuration on top, and you let it relax, and you obtain the exact configuration you started with. It's crazy. You take any configuration of sand, then you put this configuration of sand on top, and you let it relax, and you end up with the exact same configuration you started with. It's absolutely crazy. You're a mathematician and you are in ecstasy. I mean, this is impossible, but it's true. So you have this pile of sand, this one, and this is the identity. And of course, it depends on how many tiles you have on the square. So you have few tiles, it looks like this. You have more tiles, it looks like this, or like this, or like this. And this is very fuzzy, and that's good, because in the scaling limit, that's what it looks like. So there is this ideal object in the limit where the tiles are infinitely small, and that's the identity of this group. And it's a beautiful sight, you just put this thing and then you do nothing. This is doing nothing. Okay, so now we move to Teotitlán, Oaxaca. This photo is from a beautiful photo reportage I recommend by Michael Cardos, and it's called The Rocks of Teotitlán del Valle. Well, it says the Valle, the original article, but it should be del Valle. And it says woven beauty. And in Teotitlán, there is this old tradition, and they do these carpets with these beautiful coloring substances that are typically insects and fruits and all these sorts of very natural colorings. And the outcome is incredibly beautiful. I have a beautiful big one in my living room in Mexico City, and these are the famous carpets of Teotitlán. Very similar things nearby here. But anyway, Aldo Guzman, in a paper we wrote with Grisha, with Nikita, with other people, we were investigating some things and some ideas in something called K-theory, whatever that is. And then we came up with what does this element look? I will show this thing soon. And then I was walking in Teotitlán del Valle, Oaxaca, when he sends me the picture of what this element looks like. And I was next to the carpets. The group was meant to be called the Teotitlán group. Okay. So the Teotitlán pile of sand is 1, the state that it's only one grain of sand everywhere, plus the identity, relax. 1 is not a recurrent state. It's too small to be a recurrent state. So you need to recurrentize it by adding the identity. So this is 1. This is meant to be the number 1 in this universe. And notice it has this triangle coming in 1, going up to infinity corners. And now we take 1 plus 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 1. But this ends one day, and when you get to a certain number, you get back to 0, and then plus 1, because it's a finite cyclic group. It's like the hours of the clock. 1 plus 1 plus 1 plus 11 plus 1 is 0. So, or 23 plus 1, whatever you use. 23 plus 1 is 0. So it's like the clock. This group is a finite cyclic group. And this is 1. And then you add it, and you finally get to the identity. If you add it, you get to 0. And you want to ask yourself, how many times do I have to add it to get to 0? And this is for a 100 by 100 square lattice. That is not very big. You need 10 to the 603. It has 3 to the 603 elements. It's a finite cyclic group with 1 and 603 zeros of elements. It's a very large finite cyclic group. It's like clock with 10 to the 603 hours before it comes back. So it's an enormous group. It's finite group. And so, well, grows extremely fast, the order of this group. And so this is the Teotitlán order. So William Blake has this beautiful poem in Auguries of Innocence, 1803-1808, that says, to see a world in a grain of sand, and a heaven in a wild flower. Hold infinity in the palm of your hand, and eternity in an hour. It's a very famous poem by William Blake, and it's perfect for this situation. The Sandpile of size 100 is a number, has so many elements, the Teotitlán group has so many elements, 10 to the 603, that if you did one of these operations of adding 1 plus 1 in 1 millisecond, it would take you 10 to the 592 years to complete. This is way orders and orders older than the expected age of the universe. You'll never be able to do it. It's an extremely large group. The observable cosmos holds only 10 to the 90 elementary particles, and it's of the order of 10 to the 10 years. It's nothing. So, to see a world in a grain of sand, hold the infinity in the palm of your hand. So, this is exactly William Blake's poem. You know, this Teotitlán group is enormous, and it's made of carpets. You see, every one of these states is one of these carpets, and it's different. It's 10 to the 603 carpets. And you add the carpets, and you get a new carpet. And it's a finite cyclic group. Just a finite cyclic group. So mathematicians would underestimate a finite cyclic group, but it is extremely interesting. So, for example, the orders have this astounding number theoretical property discovered by our students that if you factor into prime numbers, we're obsessed with prime numbers mathematicians. Prime numbers are those that you can only divide by 1 or by itself. 4 is not prime because 2 times 2, but 7 is prime because you cannot multiply numbers to get 7. So a prime number is one that you cannot multiply numbers to get the number. And the order of the group has these two that is 1, 4, 1, 3, 1, 5, 1, 3, 1, 4, 1, 3, 1, 6, 1, 3, 1, 4, 1, 3, 1, 5, 1, 3, 1, 4, 1, 3, 1, 7, 1, etc. So it has, we can predict how many times 2 divides this enormous number. the number of primes grows linearly, and they are to the power of 1. And this is striking. What are the chances that this number are power of distinct primes? It's today we call it a conjecture. It is absolutely striking. Think about it. How did we even compute the order of the? And we have to table to one another. It didn't fit in the slide. How did we even compute the order of the group to 100? You cannot add these. I told you. I mean, you would need ages and ages of the universe to just add the elements and check when you get to the identity. We have to use mathematics, potential theory, Green functions, things like that. But number-theoretic mathematics, typically you have this in calculus, but we use this calculus over the interior numbers to get the order of this group and to get these prime factorizations and to discover that they are these primes to the power of 1, which is extremely surprising. So let's see if this works. It's a video. We are going to walk in Teotitlán. We are going to count in Teotitlán. 1, 2, 3, 4, 5, 6, 7. Let's count. This is the element 1, and then we'll see the element 2, and then we'll see the element 3, and the 4, and the 5. Of course, I won't go to 10 to the 600. I will not go to 10 to the 600. I'll stop before 10 to the 600. So, let's see if this pulls it off. 1, 2, 3, 4, 5, etc. That's the Teotitlán group. And you get this amazing topological structure. So you get these topos above these other topos. Again, because it's so nice. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 30. So this is, but you see, if you show this movie to a kid, the kid will be able to guess what 21 looks like. He will have no problem guessing. And in the scaling limit, he'll always be right. In the scaling limit, he will always be right. In the non-scaling limit, we have a phase transition around the square root of n or something like that, where we have this size n by n. But in the scaling limit, the kid will always be right. And so it's kind of funny because now there is this situation in which we can kind of, no, I have to do something. In which, this is the fifth element, for example, this is 5, Teotitlán 5. This is Teotitlán 5. And we can form this kind of graph, this kind of picture with dots of colors and lights on a graph, but it's actually the information for a topos that tells some truths over here. And then there is the classical topos of the piano axioms over here. So you have these topos of the piano axiom, whatever they are, the numbers. You have these laws of the language of the numbers, and you have the language of these lines, and they talk to each other. This language, you could say, oh, the language of the number is forcing the language of the graphs to behave a certain way. But you could say, the language of the graph is forcing the language of the numbers to behave in a certain way. And this is an interesting, so this is the sixth, and then you can guess the structure of this. And then this is -1. Look, the triangles were going off over there, going off, fifth, then you have this 2, 2, 2, 6, you have this 3, 3, 3, 6, and now you get -1, now the triangles are coming in. And you can, and so you invert the colors of your system here, you have this topos that talks about this thing, and the other one talks about the other thing, and this is -2 in the other clan. And so, but you said, I'm just talking about a finite cyclic group. Yes, I'm just talking about the finite cyclic group. Nevertheless. So there is this ongoing philosophical discussion that is top-down versus bottom-up causality. So there is this famous philosophers George Ellis and Dennis Noble. Science has untrusted the bottom-up story. Matter gives rise to life to mind, is level born from the blind dance of smaller parts. Both philosophers like George Ellis and Dennis Noble dissent. They see higher forms, organized ideas, meanings, as capable of reaching downward, shaping the motions of matter, selecting from the possible rather than merely obeying the inevitable. This is top-down causation, where context becomes cause. I will end the talk with an incredibly beautiful dot, the bottom causation, where Stephen Groffman says on the other side, no. Stephen Groffman says, that's our person for him the universe is not commanded from above, but computed from below. All pattern, purpose, and beauty emerge from laws as simple as Sandpiles laws, replayed endlessly by the great algorithm of nature. In our work, the Algebra of Avalanches, the self-organization of brains networks will live at their intersection. Top-down and bottom-up are not enemies here. And we have top-bottom causation laws. So Stephen Groffman would say, you cannot tell me this grain of sand, unless you do this enormous computation, you cannot tell me what color this square is going to be. And we have this theorem that says, I kind of can. With enormous probability, I can tell you very well for most grains what color they will be. So we have this top-bottom causation. We have this topos here, and topos dictates the colors that not deterministic Kolmogorov complexity is there. But probabilistically, if you relax Kolmogorov complexity for probabilistic algorithms, we can do it. Okay, so let's see Boltzmann. So this is the grave of Boltzmann, and this is his masterpiece, K log W. S equals K. I lied. This has one equation, this stuff. Anyway, so K log W. K log, this is a equiprobable state, so it's P log P. It's K log for the people that don't know. K log W is a fantastic formula. It tells me that entropy is this tiny number. It has to be tiny, so, because otherwise I get these enormous numbers. You're so well getting these enormous numbers. It's this tiny number, 10 to the minus 23, times the log. I'm just counting the digits of the number. I'm not counting the number. I'm just counting the digits, because these numbers are so large that I only count the digits of the number. I don't tell the number, I just count the digits. And this tells me what is the measure of disorder of the system. So, is this a recurrent state? Is this not a recurrent state? This has entropy extremely 1.999 that you would expect for it has nothing, and this has 1.768, a recurrent state. So, you see, suppose that you are captured by the Nazis, and then you are in this place, they're going to kill you, and they say, well, I'll let you go, but give you an element, a picture, and you tell me if it's in the Petri group. Oh my God, you have 4 to the n, you have this gazillion of possible states, gazillion of possible recurrent states, and gazillions, orders of magnitude law, gazillions of possible Petri states, and they give you one, and it may not look very symmetric to you, and your life depends on it. So what do you do? Well, you call Boltzmann, and this is what you do. You compute the entropy, and this is the entropy for stable states, this is the entropy for recurrent states, and this is the entropy for theoretical states, and you see these spectral lines in the entropy. And this is a tiny 10 by 10. But if you go 12 by 12, and then you go 14 by 14, you see you start kind of... And now, they gave you a very high resolution picture, so you are in good luck. Because if they gave you a bad resolution picture, it would be harder. You have more information if you have a high resolution picture. And so you keep going, and 114, and then n equals 16, and now you're in this state. And can I take number theory like this? And a number 20, and n equals 20. And now it's clear, you save your life. There's no problem. Absolutely no problem. You can save your life. You have absolutely no difficulty escaping from the Nazis. So take me next time the Nazis catch you. And you can detect number theory, of course. This is the prime 2, right? This is the prime 2. What do you can detect? The element of order 2. This group is has an element that added to itself gives the identity. This has an element of order 2. It's added to itself gives the identity. It has an element of order 4, 16, and you detect the valuation. And do you detect these elements by this method? So you can start detecting these primes. And so you could start making bets on, you have this number that's very enigmatic, but you kind of know it's product of distinct primes. And now you kind of try your ability at decoding codes. And now you are trying to find this is a prime 2. The half element in the theoretical group looks like this. 4 looks like this, 6 looks like this, 8 looks like this, 10 looks like this, 12 looks like this, 14 looks like this, 16 looks like this, 18 looks like this. And then you can prove, almost, half of a proof, we have a proof, that the order 2 element is the identity plus 2 diagonals. You can prove it. These diagonals are called a tropical curve. So to prove this theorem, that the element that added to itself gives the identity, this element added to itself is in the theoretical group exactly halfway through. It appears halfway through. And when added to itself gives the identity, to prove this theorem, you must relax in tropical Sandpiles. Well, it doesn't sound that bad. So you must relax in tropical Sandpiles. So, here is the movie. So, what do? You put a Sandpile where every state is 3, 3, 3, 3, 3, 3, 3. It's the heaviest stable state, right? The heaviest stable state. And it's recurrent. We already saw it was 3 in the theoretical group. It was the third element in the theoretical group. So you have 3, 3, 3, 3, 3, the heaviest stable state, and you add 1 grain of sand and see what happens. 1. Or 2 maybe. Or maybe 3. Or maybe 4. Or maybe 5. We'll see. Enjoy the movie. Where's the volume? Can you turn off the volume? We're missing the music. I don't know how to use this thing. One grain of sound, one grain of sound, one grain of sound. How is it going to become a deal? tape, okay. So to notice that more or less the number of round circuits in this story is more or less the number of points that I added as grain of sand on the one hand. Also observe that somehow this sample is solving an incredibly elaborate linear programming, integral linear programming problem. It's a hard integral linear programming problem. It's solving it somehow. And you can notice a lot of things, but you can also notice that the center are kind of horizontal, vertical, and diagonal. And there is this beautiful statistics studied by Calvini and Prieto. She was my master's student. And you have this rich structural boundary, but you always have this so-called balancing condition, so that, well, it's something that mathematicians call a tropical curve. It's a tropical, it's not an algebraic geometry, it's analytic geometry, it's tropical analytic curve. You have this tropical analytic curve that is non-algebraic, but it's okay. And this is the scaling limit that goes from D4 to SL to Z. Somehow, in physics you have heard of the symmetry breaks, the Big Bang and all that. And here, you can go both ways, right? So if you have the integral linear programming tropical problem, it has a much bigger group of symmetries than the squared group of symmetries. It has the group of transformations over the integer numbers that preserve the areas. You have this transformation over that are made only of integer numbers so far. So we have not used numbers that are not integer so far. So, not only that, the actual sample, even this huge sample, you could think, oh yeah, I need these big numbers, but no. If you add 1 grain of sand at a time, of these 300 million, only very small numbers will appear in all your computations. So if you are an ultra-finitist, you are very happy. If you don't believe in large numbers, it's okay. So you have these tiny topos here, you don't really even need the Avalanches. So you have these tiny topos here, and you have this other, much richer, the topos of tropical geometry. And so they talk to each other, but a physicist would say that here the symmetry breaks in this direction. You have symmetry breaking from SL to Z to D4. You have this symmetry breaking as you become more and more energetic. You see more and more, and so the symmetry breaks. But at this level of microstates, you have this tropical geometry. That's what arises. The thing that arises as the scaling limit in this regime is that of tropical geometry. So you can play this game that we had there, And then you put lots of them. Lots of them, you have a lot of fun. You keep doing this. Then you get greedy, you know, you say, I want to really try my luck. I'm going to really put a lot. And then you get this. And now, a new symmetry is arising. What is this symmetry? The symmetry of a new zeta function is the symmetry of the real numbers. You started with these small integer numbers, then you need all the integer numbers in tropical geometry. You started with these ultra-finitist numbers. You have these topos of ultra-finitist numbers, then you get, limited arithmetic, bounded arithmetic. Now you have this one with all the integers, and all of a sudden the real numbers arise. This is the Laplacian of this. And you know the statistics at the center, you realize that you have a kind of a Poisson problem, but you have enormous problems at the corners. You have enormous problems at the corners if you want to do it with a Poisson partial differential equation. So, let's get rid of the corners. Let's do it in the circle. And now we have two symmetry breakings, or two scales, or two ways of do top-bottom causation, or bottom-top causation, top-bottom causation. And so you have these three topos, the one that talks about bounded arithmetic, the one that talks about the integer numbers, and the one that talks about the real numbers. And they talk to each other. And now you have the Poisson problem. And you do lots of sand. This is one grain of sand. And for any ellipse, to solve the problem, it's a complicated linear programming problem, but you can solve it with hyperbolic geometry, integral hyperbolic geometry. You can solve it. We have solved it. We have full solution of this incredibly elaborate integral linear programming problem using integral hyperbolic geometry. Kevin is working on a harder problem because corners, remember? Triangles. He's working this extremely hard problem of triangles, and now you have this Thurston tree manifold. Now you have this bigger thing that has more geometry, that dictates the top-bottom causation for the Sandpiles. And this is lots of sand on the circle. And you don't have corners. And now you realize that you do have the Lie group emerged. So now you have the topos of the real numbers. Now you have the Lie group emerging, the symmetry emerging. And this is the Laplacian of this function for many grains of sand. Of course, using the Kalinin-Prieto statistics, you can wash out these imperfections. But aren't they beautiful? Aren't they so beautiful? They remind me of a beautiful short story by Jorge Luis Borges, 1940, called Las Ruinas Circulares, the circular ruins. Las Ruinas Circulares, the circular ruins. And Borges says, he understood that modeling the incoherent and vertiginous matter of dreams was the most difficult task a man could undertake, though he might divine that of others were but the shadow of that one. Thank you very much.
Thank you, Ernesto, for this interesting talk, and very vivid one, very artistic. We have time for short questions because we have another meeting at 11 to present also the group of Ernesto and the other groups to Bulgarian authorities, to our investment from Sanders Foundation.
I usually dress decently, not like this.
Questions?
Rafael.
If you try to define the topology, is there any kind of distance that you can define that determines, the location of those boundaries? Like, of course, I have that image, the Avalanches, that it's not that, it's way more complicated. Like, is there a topology that you can define?
It's a minimal model problem in algebraic geometry. Is the V omega in dp equals minus or plus k. This is the canonical class. And think of conic geometry. And you want this to be
a topology that
this
is the Morse flow of a beautiful Morse function that can be written a la Witten with this supersymmetric formalism. So this equation, I should have mentioned Grish and Michalkin. They have studied and are studied and have enormous success recently studying this equation in any dimension. Because up to now it was dimension 2. It gets harder, you see? But now in any dimension they have amazing success studying the minimal model problem differential equation. That's right. But yeah, you are, this is the right question to us, exactly the right question to us.
The questions?
In the construction of the ICMS, in the process of choosing some grain from one set to another, as a physicist, I would think of diffusion equation, but the diffusion from a central point is symmetric. So this symmetry that emerges is caused because of the breaking of the interval balance condition or something like that.
Well, it's an elaborate conversation. We have some ideas of how these symmetries are emerging. They have a theorem proof for the emergence of SL2 set. It's an amazing rigorous, one of the very few rigorous theorems in mathematics with this complete proof. And now we are thinking about the SL2R emerging. We have, for now, we're applying the methods of applied mathematics at the moment, and we want to get it with correct p-values and many sigmas, 4 sigma. We want to be sure for many domains with 4 sigma that we are not crazy. But of course, we have this corner issue where you saw this kind of crazy Superman's cities of solitude arising at the corners, and this has to be taken with enormous care. So a lot of interesting stuff. We can talk more if you are expert in GDs and all that kind of thing. We can talk more, and it will be very interesting.
One more question? I don't see. So let me once again also give thanks to Ernesto for this beautiful lecture and to wish further success in this research and also in the others, of course, topics.
Thank you very much.
Members of the ICM